We're going to start lab today with one of the instrumentation sections in your workbook. This can get a little bit long, so you might want to do this in pieces over the next week, whenever you get to stopping points. It is the first instrumentation section. Even though we've done mass spectrometry already, partly because this one requires a lot of knowledge about functional groups, which we really didn't learn until the latter part of last semester. I think it's probably simpler than mass spectrometry, though it does require a little bit of memorization. So surprised with that. Okay, so we'll start. Normally we do a demonstration here with some springs. I'm not going to do that for you, so you can just imagine, or you can use some rubber bands if you want. Consider a weight suspended from a spring or rubber band that is dropped and allowed to bounce. Before seeing a demonstration, predict with your group, or by yourself rather, which case below will have the fastest frequency. Fastest frequency means the number of bounces per unit time, and which will have the lowest. Okay, so hit pause, look at your options in number 1 there, and then hit play when you're done thinking about it. Okay, so you probably chose, or I hope you chose, number 1 and 4. So 1, the stronger the spring, the faster the frequency of bouncing. And 4, the lighter the weight, the higher and faster the frequency of bouncing. So these we can cross out. Model 1 takes us to resonant frequency. You've certainly learned about this in physics at some point in your education. Consider a parent pushing a child on a swing. If the parent pushes at the exact right intervals, energy will be absorbed by the swinging child, and she will go higher. If the parent pushes at the wrong time, like we see in the picture on the right side, the swinging child will not absorb energy from the parent, and the swing will not go higher. So over here, if the parent pushes at the right time, they are in resonance with the swinging of the swing. That makes sense. Anyone who's pushed a swing knows that if you push your hands when the child isn't against them, you are not in resonance and the swing will not be affected. Okay, so there you have resonance in a term you can easily understand. Frequency equals cycles per unit time, often given in hertz. And sometimes we'll see it, actually frequently we'll see it with units of inverse seconds. If the frequency of pushing matches the frequency of swinging, then the two are in resonance with one another, like we see over here. Frequency can be a measure of any repeating phenomenon. What other phenomena around us are measured in frequency? So you're probably thinking light. Light can be measured in frequency. Sound. High-pitched sounds have a higher frequency. RPM, revolutions per minute, for often like how fast a wheel turns. All of those would be frequencies. There are lots more examples. Wavelength and energy are closely related. Many phenomena around us can be measured in frequency, including ocean waves and light waves. Label the wave with the shortest wavelength and the wave with the longest wavelength. Okay, hopefully that's nice and easy for you. On the top here we have the short wavelength. On the bottom we have the long wavelength. I know that because of this distance. You can think of frequency in hertz as the number of wave peaks that pass a given point in a second. Assume the cartoon waves above are moving at the same speed and label the wave with the highest frequency and the wave with the lowest frequency. Okay, so assume that this width from here to here is 1 second, The one that goes up and down the most times is going to have the highest frequency. And this one down here is going to have the lowest frequency. Which has more energy, a high frequency wave or a low frequency wave? And hopefully you remember from physics, high frequency carries more energy. Think of it in terms of light. X-rays have higher energy than visible light because they have a higher frequency and a shorter wavelength. The electromagnetic spectrum, again, this is review. You've all seen this before. Are your answers to the previous 3 questions consistent with the electromagnetic spectrum in this table? And the fact that wavelength is inversely proportional to frequency and energy. And if you need a moment to think that through, hit pause and do so. But yes, our answers are consistent with this. Bonds in a compound, in a molecule, are like springs. Bonds stretch, bend, and wag as if they were balls attached to springs. A light wave of the correct frequency will be in resonance with a bond motion and transfers energy to this motion, like the parent pushing the swinging child. We say the light is absorbed by the molecule when that happens. So normally we would be in person and I would demonstrate with my arms what these motions up here are. So the top one, if you kind of put your arms up like a Y and pump them up and down, that's kind of like that one. If you do the asymmetric, when one arm goes down, the other one goes out, kind of like, I don't know, I think of like the song YMCA with these. And then the asymmetric bend is like you're a Y, and then your hands come together and then go back apart. And if you're wondering, yes, I'm sitting here in my office making this video and acting these out, so hopefully nobody's looking in my window. Pretend that your hands are the H atoms and your torso is the oxygen of water. Do the little water dance if you want. It's a good way to remember them. Demonstrating symmetric, asymmetric, and symmetric bend. Water molecules do all of these at once, plus some other motions that we don't see, like rotating and so on. Each unique motion adds or absorbs a unique frequency of light in the infrared range. Answer the following questions relating to the cartoon experiment below. Okay, on this we have our infrared source, which is heat. The different wavelengths and frequencies of light are shown by all these zigzag lines. Different frequencies mean different distance in the zigzag. And then we have a detector over here that can determine which wavelengths, which frequencies of light, make it from the infrared source all the way over to the detector. Notice that some of them are not coming through. What happened to the light that was absorbed by the water? So in other words, we have this one, this frequency, and this frequency. What happened to those? So yeah, it was absorbed by the water, but the energy absorbed went into exciting molecular, well, that's not a very good R, molecular motion. In other words, as the water absorbed these wavelengths of light, it started doing these things up here with greater frequency. Why are some frequencies of infrared light transmitted through the water? So the reason is that these frequencies of light are not in resonance with a possible motion of water. Again, those motions. In the diagram above, does a peak on the graph represent frequencies that were absorbed and by the water, or frequencies that were transmitted? So we see right here, detector prints a graph showing which frequencies never made it to the detector. We also see on the X right here, absorbance. So it is absorbed. This also gives us an idea of how something like a microwave oven works, where the microwave sends waves of a certain frequency through your food and causes the water molecules to start vibrating. And you probably remember that as a molecule starts vibrating more, usually it's because its temperature is going up. So that's how a microwave oven works. It causes water molecules to start vibrating faster, which then makes your food hotter. It also helps explain why your plate doesn't normally get hot in a microwave, but your food does. Which of the... we have something to fix here. This is slightly wrong. We should cross this out. It should be an NH. And over here, we should scribble this out, and it should be an N. Which of the following carbon-carbon bonds is longer? And hopefully you've chosen this one. We know that one's longer because it's a double bond. Over here we have a triple bond. Double bonds are longer than triple bonds. Single bonds are longer than double bonds. The Greek letter nu, which looks like a V, is used to represent frequency, and I've been doing that already. Label light with frequency equals A and frequency equals B above, with higher frequency or lower frequency based on the spring demonstration. Okay, hit pause and take a moment to think this through, and then come back. Okay, this one over here, we're going to see the lower frequency. This one we will have the higher frequency. Right, the stronger bond is going to vibrate like the stronger spring with a higher frequency. Onward to infrared spectroscopy. This is one of the most important tools in an organic chemistry lab. Many bonds of interest to organic chemists are excited by and absorb light in the infrared region of the electromagnetic spectrum. Essentially, what we saw before up here is duplicated down here. Okay, the detector prints a graph called an infrared spectrum showing which frequencies never made it to the detector, and therefore they're called absorbed. By convention, infrared spectra are printed upside down so the peaks look like valleys. Another thing to look out for is that the x-axis is marked in wave numbers, also called inverse centimeters instead of frequency. Since inverse centimeters are proportional to hertz, to frequency units, inverse centimeters are just another unit for frequency. Where we see a peak, or actually a valley, tells us that this particular frequency of infrared light was absorbed by the molecule as the infrared light passed through it. What happened to the frequencies of light that never made it to the detector? And it's the same as before. They were absorbed, and their energy went into exciting the molecular motions. Assume that the light hitting the detector in figure L1.4, that's this one right here, is missing light at frequency A, but is not missing light at frequency B. Based on your conclusions at the top of this page, what structural features does the molecule in the sample tube have and not have? So compare with what you see up here in question number 10. And hit pause if you need a little more time to think. So that would tell us that we have this somewhere in our molecule, and it does not have something like this. Okay, we know that because of this information right in here. It takes us to the IR spectrum and characteristic IR absorptions. An infrared absorption frequency table can be used to assign peaks to functional groups on the structure of an analyte molecule. Again, analyte, that word means that's the molecule that we are interested in and we have put into the IR spectrometer. So analyte is the molecule of interest. Label each peak marked with an arrow on the spectrum with a type of bond found in the molecule in the box. Okay, so let's start with this one right here. Okay, this big broad peak clear on the left. So we're going to start and look at what its wave number is. And this looks like it is around 3,300. So we're going to come up here to our table and look for something around 3,300. So there are two possibilities. We see 3,300 fits in this range. It is also somewhat in that range. However, right here I see the word broad and strong. Now this peak here, I would call that broad and strong. These here are not broad. They're pointy. So that word is pretty important. So that indicates to us that this peak is due to an OH. Okay, one other thing to notice, see that the line is between the O and the H. It's that specific bond that has that absorption, that's in resonance with light of this frequency. That can be sometimes a little confusing as we look down at, for instance, here. So let's compare this one and this one. They both say alcohol. The difference being this one at the bottom is talking specifically about the carbon to oxygen bond of an alcohol. The one at the top is talking specifically about the oxygen to hydrogen bond. They're different types of bonds, therefore they'll have different frequencies. This one is harder to recognize because it's not broad and strong. So this right here, this is one of the most characteristic, easy bonds to recognize in an IR spectrum. So keep an eye out for those. If it's broad and wide like that on the left side, you have an alcohol. All right, I would like you to hit pause and to identify each of the remaining arrows down here as best you can, and then come back and check your answers. Okay, here we have the sp2 hybridized carbon to hydrogen bond. Next we have the sp3 hybridized carbon. If you need to refresh your memory on your hybridization, do that now because we'll talk about it a lot. Here we have a C double bond C, and here we have the other end of our alcohol. Again, notice the difference between this alcohol and this alcohol. They both refer to this right here. It's just that this bond is right there. This bond is right there. Number 15, checking our work. The peak for an alcohol bond in table L1.2 is described as broad and strong. Did you label the broadest, strongest peak on the spectrum with an O-H? And yes, we did. They describe the peak as udder-like, which I think is kind of funny. The fingerprint region of an IR spectrum is often so crowded with peaks that it is hard to make assignments. In this case, which assigned peak falls in the fingerprint region? So we see the fingerprint region is this over here. This one looks actually pretty simple and nice. If you get a real IR spectrum, it is often so full of lines that are so crammed close together, it's really difficult to make functional group assignments based off of it. However, it does have a use, which we'll get to later. So the fingerprint is the COH bond. Now, speculating, why do you think this is called the fingerprint region? And partly it's called fingerprint because it's really complicated, but the better reason is that the fingerprint region is unique to a certain molecule, just like your fingerprint is unique to you. You can't necessarily look at your fingerprint and determine much of anything about you. However, you can compare your fingerprint to one that you left somewhere and match it to you. I mean, that's why it's useful by the police in identifying, who was at a crime scene. It's similar for molecules. Even though you can't identify specific functional groups very easily in the fingerprint region, you can use it to confirm. For instance, if there's a unknown white powder in the back seat of somebody's car and the police think it's cocaine, they can run a known sample of cocaine and get the IR spectrum for it, and then they can run the unknown white powder in the back of the car. If the fingerprint region matches, likely it's cocaine. If it doesn't match, it's not cocaine. Okay, so the real term for the fingerprint region, two IR spectra of the same molecule should have matching fingerprint regions. Even though exact peak assignments are normally not made in this region, it can be used to identify a unique model, much as a fingerprint is used to identify a unique person, if you have a standard to go off of. Okay, you need to memorize this table. I want you to be doing lots of practice problems, and so that will come somewhat naturally. I think it's pretty helpful to make a copy of this. Normally when you all are in class in person, I give you a card with that, and I'll give that to you when you come in person. As you're doing homework problems, it might be helpful to take a picture of it on your phone and put that on your computer screen or something so that you're not having to flip back and forth so often. This is also duplicated in the IR section of your textbook, which is much more in-depth than this activity was and will answer a lot of your questions. The IR spectrum below goes with one of the four structures below. Circle the structure that goes with the IR spectrum. So we are going to start sorting through this. First off, I'm going to look and see if we have an alcohol. If we had an alcohol, there would be something that looks like that right there, that broad, strong peak. We don't have that, so therefore we know we don't have this. We can narrow that one out. I see a peak right here. So flipping back to our chart on the previous page, I'm going to assign that as an sp3 peak. A little ways over, I see another interesting peak right here, and that looks about, I don't know, around 1540 or so. So checking out what that could be, it looks likely that, sorry, that I didn't mean 1540, that's closer to 1700. It looks like a carbonyl. That third from the bottom, it says strong, and I would say that this peak here looks strong. So I think that this is carbonyl. So we have, that's going to narrow us down. If we have a carbonyl, it has to be one of these two things. We need to look now at if we have sp2 hybridized carbons. So these two carbons here, these are sp2 hybridized. To have an sp2 hybridized alkene, we would need a peak around 3050 to 3150. And so that would be in this range here. We have no peaks there. So therefore, we know we don't have that. So that must mean this molecule is this one right here. Okay, we can also narrow out the amine. We know we don't have that peak, 3100. That would fall right in this range also. We don't have anything there. On this one, an alkyne should be at 3260. Again, we don't have anything in that range, so we know it's not that one. And so on. So, there we go. We know we have that. Match peaks in the spectrum above to two different types of bonds on the structure you have circled, and we've done that. You cannot draw the structure of an unknown molecule based only on information from an IR spectrum. Summarize what information an IR spectrum can give you about an unknown molecule. Okay, here I want you to hit pause, and I want you to think through this really carefully. An IR spectrum tells us one thing. It tells us which functional groups are present in a molecule. It does not tell us anything about their arrangement. So for instance, we could have this molecule. We could also have this molecule. An IR would not be able to tell us anything about the differences between those two molecules. All we know is that we have a carbonyl. We don't know anything about the quantity of carbonyls or anything like that. So IR spectroscopy is really useful for confirming identity if you have a standard, like with the example of cocaine. It's also really useful if you're doing organic synthesis and you want to confirm this certain step was supposed to say add an alcohol to your molecule. You can run IR samples on your intermediates to kind of check your progress to see if you're actually adding the functional groups that you want to be adding. If you have an unknown, it can be used in tandem with some of the other techniques that are shortly after this, like mass spectrometry and NMR, to help you kind of get lots of information about the makeup of your molecule. The mass spectrometry tells you the mass of it, so you know the size. The NMR, which we haven't learned about yet, is going to tell us how those carbons are all assembled into being one molecule. Okay, so that is the basis of what infrared spectroscopy is. I would like you to do exercise number 1, which has 5 different spectra. So what you're going to do, we've identified one of these already. We identified this one. Now the rest of these correspond with these spectra. I want you to take your time, match up each molecule with each of these spectra, and that will be your lab write-up for this week. Okay, I do want to go over the big picture and common points of confusion before we wrap this up. Big picture, how do chemists know what molecules look like if they are too small to see even with the most advanced microscope? The answer is spectroscopy, which we are learning about now. Basically, we shine light of various frequencies on a pure sample of a molecule, and based on what happens to that light, we can make various inferences about the structure of the molecule. IR spectroscopy is the first of several spectroscopic methods we will study in this course. The next one is called NMR, is much more powerful and will, unlike IR, help us to elucidate or determine the entire structure of some simple molecules. Now, something I didn't mention before, the IR spectrometer has a detector that can detect if light is reaching it or not. It has a source, which is pretty much a light bulb that gives off infrared rays of heat. There's something called a diffraction grating inside the IR, and essentially it looks like this. Okay, and it's, well, I can draw this a little bit better. It should actually be curved. You can kind of think of it like a prism, and it's on a hinge. So this can rotate, it can go this way, it can go that way. And as the infrared spectrometer is running, you can actually hear it moving around. So here's our source, which is a light bulb, and through some lenses, it is focused down on a certain point. So the light comes in, and as this diffraction grating moves, the light is then separated into its wavelengths. So we would have, frequency of this going off this way, the next frequency going off this way, the next frequency, and so on. As the diffraction grating moves, these different wavelengths then pass through the sample. So only one wavelength at a time is passing through the sample. So that's how the detector knows which wavelengths of light come. You can't just shine all of them at one time. The detector would not be able to tell you which one is which. So this is not a very good drawing, and I'll try to find a video of how this actually works if you're interested. But it's actually very simple. It's ingenious, but it's very simple. So essentially, the diffraction grating takes the source of infrared light, turns it into a rainbow of infrared light, and only shines one color through the sample at a time. When that one color disappears, we know the sample has absorbed it. Okay. I don't know that that's terribly important for us right now, but I was always really interested in how these things work. And you guys might be too. One big problem with infrared for students is that the peaks are upside down, making the peaks look like valleys. I don't know that there's too much to be confused about that, but it can be strange. The biggest problem with IR for students is that they assume the following. If there is a peak on the spectrum in a given range, there must be a specific functional group in the molecule they found on a table that corresponds to that frequency. Instead, IR peaks should be used as corroborating evidence of the existence of certain functional groups. The only possible exception to this rule is the existence of the OH, and the carbonyl functional groups can usually be definitively read from an IR spectrum. So what that's saying, just because there's a peak on your IR spectrum doesn't necessarily mean that there's a functional group associated with it. However, it's good evidence to use as support of your molecule having a certain functional group. Another problem is the units can be confusing. Wave numbers or inverse centimeters are simply measures of frequency. Higher wave number means higher frequency. Students sometimes assume that they should be able to deduce the structure of an unknown molecule simply by looking at the IR spectrum. As we will later see, molecules are identified by using a combination of various different spectroscopic techniques. IR simply tells you whether certain characteristic bonds, functional groups, are present in the unknown molecule. It does not tell you anything about where they are. So that's a common way that students make this more difficult than it needs to be. Okay, we're going to wrap it up there. Throughout the week, work through these 5 exercises on page 267 and 268. Try not to do them all at once, because I think it's better practice for you if you spread it out over at least a couple days or a couple different time periods in one day. If you have any questions, please let me know. I'd be happy to make additional videos clarifying some of these. And when you get back to class in person, I would also like to go over them together. All right, good luck, and let me know if you have problems, and I'll